And now to set up the integral, we have to determine the limits of integration, which are the upper and lower bounds of the integrals. And I've decided for this particular problem, I'm going to be integrating with respect to z first, then y, then x. And if I'm going to integrate with respect to z first, I have to find the limits of integration for the z-axis first. And so that'll be given by the equation. So the first integral with respect to z, the lower bound is going to go from when z equals 0 to when that value reaches 6. And so that will be given by the equation z equals 6 minus 2x minus 3y. And that's derived from this equation up here, which is the region of the equation of the plane. And so that's my first limit of integration with respect to z. So then we write the rest of the equation. So that's 2x, and then with respect to z, so that's dz. And then the rest of the equation, we'll call that dA. And now using basic integration, since we're integrating with respect to z first, we're going to leave any other variable constant. So this 2x will remain constant. And so the integral of dz is z. So this can be rewritten as 2xz from 0 to 6 minus 2x minus 3y dA. But now dA can be rewritten as dy and then dx. As I've decided up here that I'm going to integrate first with z, which I already did, and then with respect to y, then x. Now using the fundamental theorem of calculus, I can substitute in these lower and upper bounds for z, and that'll give me the equation 6 minus 2x minus 3y dy dx. And now that I have my x and y variables here, I can now determine the limits of integration for the rest of the region. So first with respect to y and then x. And as I showed you earlier here, this is the xy plane. It's kind of the bottom surface of the region E. And so using the line here, which we found earlier, we can determine the lower and upper bounds for y with respect to y. So for the y, in the y direction, it'll vary from 0 to negative 2 over 3x plus 2, and that's this point up here. And then it'll be with respect to x, and so that'll be from 0, and x goes to 3. And so that's the rest of the setup for the triple integral. We've already integrated with respect to z up here, and then this is the rest of the setup for y and then x. There's this up here. And now using integration and FTC, our final expression down here should be 1/3 x to the 4th minus 8 over 3 x to the 3rd plus 6x squared from 0 to 3. That's with respect to x. Now using FTC, plug in 3 and 0 for x, and the final answer is 9. And so here we can see the different implications of varying the order of integration in which we integrate and evaluate the triple integral, and using basic algebra and drawing out the different graphs and portions of the region E shown here, we're able to use all of that information to find the area underneath the plane 2x plus 3y plus z equals 6, which is 9.